Okay, so let's look at titrations. So titrations are vital in acid-base chemistry. Titrations basically allow us to work out the concentration of an acid or a base. You must have done titrations before. They are very fiddly because you've got to make sure you're reading it accurately. You've got to be making sure that you have the right substances in the right places and that you're monitoring for an endpoint. But anyway, so in the burette, you have an acid or a base with a known concentration in the burette. And you have an acid or a base, depending on which way around you're doing it. Obviously, if you've got an acid in the burette, you'll have a base in the conical flask and vice versa. But in the conical flask, the substance, whatever substance in there, you have an unknown concentration, but a known volume in the conical flask. And you add your indicator in there. So it might be, for example, 25 centimeters cubed of solution in the conical flask. And then what we do, we add the chemical in the burette into the conical flask until we get a change in the colour of the indicator. And this is known as the endpoint. This is the point where you stop titrating and you measure how much of the substance you've added. And we add it drop by drop near the endpoint. You don't just, you've got to go really, really slowly. Otherwise, because it's one drop can be the difference between the endpoint and not being at the endpoint. So that's how precise it is. You've really got to go quite slowly towards the end. And you read how much chemical was added from the burette to neutralise whatever chemical's in there. And we always read from the bottom of the meniscus. So you always read at eye level. So here's a diagram here. And you can see that we have a meniscus here, which is just it looks like a semicircle. You've got a top layer and you've got a semicircle underneath. So you always read at the bottom of that meniscus. So you can see here, this is reading 20 centimeters cubed, not 19.8. Okay, so that's really, really important. Okay, so record your results to 2 decimal places and repeat until you get to 2 results that are concordant with each other. And what we mean when we say concordant is that they're within 0.1 centimeters cubed of each other. So you've got to get results that are fairly close. You can't have one at 20, one at 21, another one at 27, because you've got results that are all over the place and you can't be confident of what the actual value is. So you keep on doing it until you get 2 results. So if you get 2 20s, for example, then you know the 22 and 27 are just anomalies and you shouldn't count them. Okay, so let's look at titration curves. So the following graphs, these show a pH against the volume of base added from a titration. So we've seen the mechanics of a titration. And what this shows is different combinations of weak and strong acids and bases. Okay, so what we're going to look at is the first one, which is strong acid, strong base. The graph starts at pH 1. So you can imagine in your conical flask you have an acid solution in this example, because what we're doing is we're adding a base to this conical flask and the pH is rising and rising and eventually it jumps up and becomes basic because we're adding the base to it. So there comes a point where we get to an end point. So this is a very strong acid, strong base, a very pronounced S shape here. So a strong acid, weak base. So we're adding a weak base to a strong acid that's in the conical flask. So it starts off low pH because it's a strong acid, and we're adding the weak base. And because it's a weak base, it doesn't rise as high as a strong base would. So we get a shorter length. A weak acid, strong base. So because we start with a weak acid, the curve is a lot higher up the graph because a weak acid is somewhere around a 6, 5 or a 6, somewhere around there. So we start from there, we add a strong base, and that rises to a high level, higher than what it was here before because it's a strong base. The next one is a weak acid, weak base. Now there's barely any change. There's not a very well defined endpoint here. A weak acid and a weak base, there isn't much difference in their pHs. So it's going to be really difficult to get an endpoint, a nice clear endpoint on titrations like this. So you can see what you've got to be able to do is identify what type of titrations they are just from these graphs here. So let's have a look at some of the features. So we have something called, on these graphs, you have something called an equivalence point or an end point. And this is on the vertical part of the S-shaped graph. So at this point, the acid has been neutralized fully by the base. and the sharp vertical rise shows a rapid change in pH, and that's why you've got to add your substances drop by drop, because it takes a very small amount when you get near to that point there, and the pH completely changes. And you can try it next time. You can see if you have a pH meter in the actual conical flask, you'll see the change in pH. And at this point, we assume that the amount of H+ ions in there is the same as the amount of OH- ions. So we have the same concentration of the respective ions at that point. And that means it's neutralized. We don't have more H+ ions than OH- ions. The change in pH is smallest when using a weak acid or weak base together in a titration. So we'd seen that on the previous graph. There was a very small change. And so in this example, with the blue line, what we're seeing is we're starting off with a strong base in the conical flask, and we're adding an acid. So the strong base has obviously got a high pH, and that starts off high. And as we add the acid from the burette, it starts to drop, and you get a massive change in pH, and eventually it becomes, all of a sudden, it becomes more acidic. So this is just showing the other way around. So it is very important, which way the graph goes will tell you what's in that conical flask. So an indicator is quite a useful thing then, because if you add two colourless liquids, you have no idea where that endpoint is, because you're just adding two colourless liquids together. So an indicator is really useful because it tells us where that endpoint is, but you have to choose the right indicator. You can't just be picking any old indicator here. So a suitable indicator must change colour entirely within the vertical part of your titration curve. And obviously the vertical part depends on what type of titration you're doing, as you've seen with the 4 different graphs before. So you can see here, in this example here, we must choose an indicator that changes completely between a pH range of 3 and 10. Anything outside that range, and we're not necessarily going to find the endpoint. So there's a variety of indicators that can be used. However, 2 of them which are the most common are methyl orange and phenolphthalein. So try and say that one quick. So phenolphthalein. So you can see here we've got colour change for methyl orange is somewhere between pH 3 and pH 4.5, which fits perfectly within our range here. Phenolphthalein changes between 8.2 and 10. So that one changes as well. So we can use either of them indicators within this titration. And so what you can see is a colour change that's happening between them. So for methyl orange is red at low pH and yellow at high pH values. And so this can be used for strong acids and strong bases, or strong acids and weak bases, because they fit within that range. Phenolphthalein is colourless at low pH and pink at a high pH values. So it can be used for the following, which is a weak acid and a strong base. So it can be used for that type of indicator. So you see, the choice of indicator is important. So when you're doing this in an exam, what you've got to look for is that zone in that vertical part, and select the right indicator. Now, you'll see weak acids and weak bases, they have no sharp pH change, and so no indicator is suitable, so we must use a pH meter for that type of titration. It's not the best titration to do it on because of the very limited scope that you have to measure the pH. So really what we've got to do is measure the pH, plot that on a graph or record it down, and then plot the graph to see where you end